If you have collected your data, the next step is to analyze your data and to run the necessary statistical tests so that you can come into a particular conclusion. Maybe you are researching about drug X is much more effective in lowering blood pressure than drug Y. Since you have collected your data on how much drug X lowers blood pressure, you have to do your analysis and do your specific statistical testing to come to a conclusion. Now, the goal of data analysis is to basically to transform raw messy data into meaningful insight. Real world data, real life data is known to be messy, is known to have a lot of missing values, inconsistent values, some errors, some invalid entries. The goal of data analysis is that you want to transform this raw messy data into understandable forms. You want to turn it into something insightful, something that can actually tell a story. It is not enough if you are performing an experiment or doing a particular research and you have all your values just stated like that. I am not trying to show if there's any change, if there's any reduction or there's an increase, or there is anything the data is actually speaking of. You cannot do so without first of transforming that data, cleaning that data, and then analyzing data, right? So the process of data analysis basically is to clean. You have to remove errors, duplicates, missing values, inconsistent values, illogical errors. You have to remove errors. So that's what we call data cleaning. Then you describe. Describe is to summarize what you have, because most times you have more than 1,000 entries, more than if you are doing questionnaire, for example, you are collecting more than 200 respondents. You have to summarize your data. You have to describe your data briefly. And what we use to describe this particular data is what we call descriptive statistics. So first of all, you do your data cleaning, you describe your data, you summarize what you have, and then you infer. To infer is to make conclusion, is to draw inclusion from. So to infer is to make prediction about a bigger picture. So don't forget, the process of data analysis is to clean or to transform, any of which you want to use, to describe, that is to summarize what you have, and then to infer, to come to a conclusion after you have run the necessary testing. That's what we call the necessary statistical test. Now we use specialized software such as SPSS, which stands for Statistical Packages for Social Science, Stata, R, and Python. These are programming language. They are much more preferred over manual calculations to ensure accuracy and reproducibility. So even if you have, let's say, a particular data on paper, you would make mistake, or it's not be much more effective if you are to use formulas and to run your calculation. So we have programming software, or we have inbuilt software that are used for statistical testing that can make the work much more effective. And a side note is that there are four main types of data analysis. We have descriptive analysis, which describe what happened. We have diagnostic analysis, which describe or analyze why something had happened. What are the trends? Then we have predictive analysis, which would use the existing data to predict the future, right? And we have prescriptive analysis, which shows how it will happen. How will it happen, right? So those are the four main domains of data analysis. Of course, we have more domains. We have regression and the likes, but the core of this particular session is basically just data analysis in itself. Now, we'll be looking at descriptive statistics. We're looking at the steps of how you can analyze your research data. Descriptive statistics. Before you can analyze, you must first describe your participants. And of course, from our mathematics, basic statistics, we know that for descriptive statistics, we have measure of central tendency and the measure of dispersion. The measure of central tendency, which involves the mean, the median, and the mode. The mean is the average, which is the average age of a participant, for example. The median is the middle value that is best for skewed data, like an income. So skewed data does not follow, a normal regular pattern. It is not normally distributed. We'll talk about that in a second. And we have the mode, which is the most frequent value in the given data set. So we have the measure of central tendency, which involves the mean, median, and mode. And then we have the measure of dispersion, The measure of dispersion talks about how spread the data are, how dispersed the data are. So we're looking at parameters such as standard deviation, SD, which speaks of how spread out the numbers are from the average. And we're looking at the range, the difference between the highest and the lowest value. And we also have variance, how the data are varied from each other and the likes. And now look at this particular graph. It shows the number of books that is read in the last year or in the previous year. And here we can see the frequency tables, or the frequency value. That means how frequent this number of books are being read. And we can see that this is a normal distribution. A normal distribution is one in which it has the mean, median, mode on the center. The data set or the data is normally distributed, and it has a perfect dumbbell shape. You can see that for here, for this normal distribution curve, of which the x-axis is not the given parameters but the standard deviation. And we can see that here we have the mean. We have one step away from the standard deviation to be 68.2%, two steps away from the standard deviation to be 95.44%, and three steps away to be 99.72%. The remaining ones are actually negligible, and they give chance for other variants of data. So normal distribution is just saying that if I'm to get, for example, the height of 10 people, how am I sure that this particular height is normally distributed around the mean, surrounding the mean? How am I sure that there is no outlier? An outlier is an extreme value. For example, if 10 people are to measure their heights, and to say, okay, the average height is 170 centimeter, then I'm expecting the height of each individual to be around 170 centimeters. Some can be 169, some can be 165, some can be 168, some can be 169.9, some can be 171. But it has to be centered around the mean, normally distributed around the mean. But if I'm seeing something like 200, that's an outlier. That data is different. So it's going to skew this particular curve either to the left or to the right. I'm not going to go more details into that because that's like for advanced class, but I'm just going to be touching the basics. Now, before we talk about dependent and independent variable, let's look at a particular data set. It's already being prepared. If you look at this data set, you can see that where we have the participants ID, which is there are about 20 participants. We have the age of the participants. We have the study hours per week. We have the sleep hours. We have the attendance and how many percent attendance they reach for the entire semester, the entire period. And we have the exam score. So now, if this is a research data that I collected, I'm looking at the study habits among students, how their study hours correlates with their exam score. What I want to run here is that I'm going to describe my data. I'm going to run a descriptive statistics. Now, I can either put the data in Excel to run a descriptive statistics, and I can also use formula to infer, but I'm not going to go deeper into that. I'm just going to, see if I can help do some descriptive statistics to this data by finding their mean, finding their median, finding their standard deviation, and also see if I'm still going to plot some graph. Most times you want to summarize your data in graphs, in bar charts, in histogram, in pie charts. So let's go further. Basically, working with Excel, we have the rows and we have the columns. These are the columns and these are the rows. And you can see this is C2 and this is C21. You can watch some videos or take some tutorials on how to use Excel. So now I use formulas to just get a sum total of the mean. So I can say equal to, and don't forget that the mean is also called the average. I guess I want to find the average. It's going to pop out here. The average from the column, from the cell. So where the column and the row intersect, they are called the cell. From the cell C2, so I'll write it here, C2, to, I have to put my colon, that's all the way to, you can see that it's already highlighted here, all the way to C21. I want to find the average study hours per week for each given student, all the way to C21. So I'm going to write C21. You can see it has highlighted everything, and I'm going to close this, and then I'll press enter. See, I found my mean. I'm just going to highlight this to write mean. I found my mean to be 12.18. That's the total, the average study hour per week. I can do the same for study hours, for attendance, for exam score. But instead of me just typing out each of them like this, I can just use a few. I can drag this, right click, and just, put this under. So it have gotten the mean for the study hours, for the attendance, for the exam score. Now I can also find my standard deviation and also my variance using the same formula. Let me put here as standard deviation, standard dev, right? I'm still going to use formulas that's equal to standard. So this is standard dev dot s, estimate standard deviation based on samples. So I'm going to click that, and then still the same thing again, C2 all the way to C20, or rather C21, so it can cover everything. And then I have 3.7, can approximate it, that's 3.7. And I can also right click this to the end, that it can give me my standard deviation for everything. So what I'm doing here is that I'm summarizing the data. What is the average for the entire study hour per week? What is the standard deviation? I can also find the variance and the likes. Now, if I want to plot a graph, I want to visualize, I can just Control A, click on the entire table, and say I want to go over to plots, to insert a graph. You can actually pick, a clustered column graph. Let me just pick this one since it's being recommended. And then you have a pivot chart and something that bring out the core thing. So here you can see the age and the sum total of the exam score. So age 19 got the highest exam score as compared to age 20, and also you can see a summary of the standard deviation. You can also remove standard deviation if you want to. This is your pivot chart that you can add anything you would want to add. You can remove standard deviation, or you can add, let's add sleep study hours per week. I can see that the graph will change as you are adding any of the given parameters in your data sets. You have to remove the standard deviation and the mean from your original data, because I kind of highlighted everything so you can see the trends. And that is all for descriptive statistics, but we don't necessarily use Excel. Excel is used for like basic levels. We use specific software to run both descriptive in a much easier manner and to run inferential statistics. Now let's continue over to some of the given understanding that we need to know in this. Yes. Now we have spoken about descriptive statistics and normal distribution curve and everything. Let's look at variable. A variable is a characteristics, a feature that can take on many values. If I say height is an example of a variable. It can take on many values. It can take up 170, 180, 100, 0, um, 9, 10 centimeter, at different units. If I say weight, it can also take on many values. So age, weight, height, blood pressure, Anything that can take up any value or any characteristics is what we call a variable. Now there are two main type of variable. We have the independent variable and we have the dependent variable. The independent variable is the variable that is changed. The variable that is changed, the one that is, that is being controlled. So, for example, the amount of water added to a plant. The amount of water here is the independent variable. It is changed. It is being manipulated. It is the one the researcher or the observer is, is using. It is one that is changed. While the dependent variable are the variables that are affected by the change. So you can say the size of plant, the number of leaves, whether the leaves are dead or alive. So I can give a research topic. Drug X causes a significant reduction in blood pressure among elderly patients. In that particular research topic, you can find which is the independent variable and which is the dependent variable. The independent variable, that is the one that is changed, right? The one that we can actually manipulate, we can cause an increase or a decrease, is the drug X. That is the independent variable. Now, the dependent variable, the one that is affected by the change, or the one that is affected by the independent variable, the dependent variable, the one that depends on the independent variable, in this particular research question, is the blood pressure of the patient and the patient in itself, the factors that are of the patient and of blood pressure. Now, in looking at analyzing data, you have to draw you have to propose a theory that your research question wants to answer, because we don't just collect data or analyze data for the sake of analyzing. We collect data, we analyze data to clean data, to, of course, summarize and to infer, that means to come to a conclusion. So we defined our core theories, and this is what we call hypothesis. An hypothesis is a theory that needs to be proven. And we have two types of hypothesis. We have the null hypothesis and we have the alternative hypothesis. Now, the null hypothesis is a statement that proves that there is no significant difference, there is no correlation among any given parameter. While the alternative hypothesis is the one that states that something is happening in this particular data set. So I can go back to this my research question, that does the amount of water causes an increase in the size of plants, in the number of leaves, and the health of the plants? That is my research question. I can draw my hypothesis and say the null hypothesis is that the amount of water does not, that means it is invalid, it is null. It does not cause an increase in the size of plants or the number of leaves, or does not affect the health of the plant at all. That's my null hypothesis. My alternative hypothesis is the true value, is the one that says that the amount of water is correlational or causes an increase in the size of plants, in the number of leaves, and in the health of the plant overall. So now I'm looking at the evidence. So the purpose of drawing the hypothesis is to give our theory, is to propose a theory that we can either approve or disprove based on the given evidence, based on if there is enough evidence on our research that the null hypothesis is true, or the alternative hypothesis is also true. Now, if you are going to talk about hypothesis testing, after drawing out your conclusion, your null hypothesis, your alternative hypothesis, we now have what we call the p-value. The p-value is also known as probability value. So let's say I have a given research question. I'll still use the drug for blood pressure now. My research question is that drug X affects blood pressure, or drug X causes a significant reduction in blood pressure. That's my research question. My null hypothesis would be that drug X does not cause a reduction in blood pressure. While my alternative hypothesis would be that drug X causes a reduction in blood pressure. Don't forget that null means nothing is happening, there is no relationship, there is no significance, there is no correlation. But my alternative is saying that something is actually happening. Now, what does p-value mean? p-value is the number that quantifies that the likelihood that the null hypothesis is true. The likelihood that something, there is no significant difference. There is no evidence that something is happening in this particular data set. So the p-value just reflects the likelihood that your data occurred randomly. Now, a small p-value would mean that the null hypothesis should be rejected. That means something is happening. While a larger p-value would mean that the alternative hypothesis was actually correct. Now, I don't want to confuse you with these parameters, but just follow me as we break down what p-value actually means. Now, that's when we're entering into inferential statistics. Because for you to answer your research question, to describe is not just enough. You cannot just conclude that, oh, because the mean is higher, the standard deviation is high, then there's a correlation. Let's say drug X reduces blood pressure by 5 millimeter of mercury, and drug Y, or the standard treatment, is probably by 2 millimeter of mercury. What is the probability that such results might be happening by chance? That is why we now have p-value and we have inferential statistics. So it's not enough to describe the data, to describe the mean, to describe the median, or to describe the mode. We should and always infer. So we should perform the necessary hypothesis testing. You have to test your hypothesis so as to ensure that there is enough significant evidence for your given data. Now, the p-value is the most famous number in research. It is the probability value between 0 and 1. And p-value less than 0.5 means that your result is statistically significant. That means your result does not just happen by chance. Let's say that drug X is reducing blood pressure in a given number of population, and it reduces blood pressure by 5 millimeter of mercury in 10 people. If my p-value is given to be 0.05, that means that it did not just happen by chance, that there's a significant evidence that drug X actually works. I'm being careful not by saying that p-value is a determining factor that my drug work or my drug does not work. It just presents the evidence. It does not mean that something is working or something does not work. It is just based on the evidence level. So I can say now, looking at this research question here, that the effect of motivation on employee performance, right? The independent variable is, of course, motivation. That's the one we are changing. That's the one we are implementing. While the dependent variable, the one that is being affected or that is being changed, is employee performance. So I pose a research question. Does motivation have an effect on employee performance? My known hypothesis would be motivation have no effect on employee performance. My alternative hypothesis would be motivation has an effect on employee performance. Let's say the probability of all employees who was motivated that was performing better was 0.5. So out of, let's say, 100% of the data sets, 50% was performing better. So I would say this is a good thing. But then the p-value has to tell us what could have happened if motivation was not there. That means 50% of them performing better. In my own sense, I'm seeing that my result is actually working, like something's happening in this particular data set. What if they were due to chance? What if they were due to other factor and not necessarily my independent variable in itself? That's what the p-value is answering, or that's what the p-value is saying. P-value is saying that what is the probability that the result you are seeing in performance was because of chance, such as other things like salary or the working hours, and not because of other things or motivation in itself. So we want this probability to be very low, so we can attribute the difference of the performance to motivation. So I can say in my research now, 100%, I want my p-value to be 5% in percentage, that's 0.05. I want my probability value to be very low, so that my remaining 95% would be that is actually what my result is saying. So the p-value has to be very low, so that I am sure that if the null hypothesis is true, my results could not have been random. So the extent to which the results could be other things should be as low as possible. So I'm looking at the probability of which any result I'm seeing, anything I'm seeing at all, is going to be due to chance in my 100% of my results. to be as low as 5%. That's the threshold. To be as low as 5%. If I'm doing a research, for example, and I'm saying that my p-value is very low, it's actually a good thing. That means that the probability that I'm seeing any results by chance is within the 5% threshold. Are you understanding me? If the p-value is less than 0.05, you are to reject the null hypothesis. That's reject the fact that there is no difference, there is no evidence. But if the p-value is greater than 0.05, we are not to accept. And mind the use of language now, we don't accept. We either reject or fail to reject, because this is not based on the fact that something is working or something is not working. It's based on the evidence level. So we either reject null hypothesis or fail to reject null hypothesis. I don't say accept. We don't say accept. That is not statistically correct. You get. So if the p-value is less than 0.05, that shows that there's a significant difference, and we reject the null hypothesis. But if the p-value is greater than 0.05, that shows that we fail to reject null hypothesis. That means null hypothesis is true. Now, coming to different type of errors, type 1 error, type 2 error. If you're going to look at this here, if let me give for example, I'm saying that drug X have an effect on blood pressure, right? Think of it like this. For the type 1 error, or what we would know as the alpha error, I am rejecting the null hypothesis when it is actually true. So I'm saying that the drug is working, but in reality, it does not work. So it's more like you are a judge and you are sending an innocent person to prison. So it is very, very dangerous. Just imagine that you are approving a cough syrup and you're saying that this cough syrup shows better results in treating cough. But what if it was just a placebo effect? What if it was never real? What if there is no evidence that shows that the cough syrup actually works? You are going to endanger the health of many people. So the type 1 error or the alpha error is what we call the false positive. Don't forget that your alpha value is 0.05. That is your threshold, right? That's your now the reason why we say that the p-value should be less than 0.05 is because we are setting an alpha value, a 5% risk that we can accept. So if you want to, some people use p-value to be 0.01, that means 1% for much more stricter research, so that they can accept at least 1% risk factor. That is to say that, okay, at least any 1% probability that we are seeing is given to the fact that the p-value is that low. So any other one we are seeing again, apart from the 1%, the 99% is certain for sure that this actually work or this actually have an effect. For the type 2 error, we call it the false negative. It's accepting the null hypothesis when it is actually false. So it's saying that the drug does not work, but when in reality the drug works. This one is not as serious as type 1, you get. So it is more like you are a judge and you are letting a guilty person to go scot-free. So it's also very, very, indicative. For example, let's say you are saying that you are testing a new drug, let's say a new anti-cancer drug or a new technique, and you are saying that, oh, you have rejected it, it does not work. Meanwhile, in reality, maybe your sample size was small. Maybe your research, the method were kind of invalid. It's not reliable. So you have rejected the null hypothesis when it is false. When in reality it actually does work. That's what we call the false negative. That's the type, the type 2 error. Now let's move further to choosing the right statistical test. Now don't forget that I said that the mean, median, and mode, they are not enough. Those descriptive statistics are not enough to come to a conclusion. You after you have run those descriptive statistics, you then have to, you know, um, come do your state your hypothesis, state your null and your alternative hypothesis. And after you have stated your null and alternative hypothesis, you then have to run the right hypothesis testing or the right statistical testing to infer, to draw to a conclusion. So we have different types. We have the t-test, which compare the means of two groups, such as blood pressure in men versus blood pressure in women. We have the ANOVA analysis of variance that compares the means of three or more groups. We have the chi-square that compare categories. No, we have nominal data, we have ordinal data, we have continuous, we have discrete. I've explained those ones before. Now, chi-square is comparing categories, the number of smokers versus non-smokers, or category of smokers versus non-smokers, students who did well, students who does not did well, student that goes to public school, student that does not go to private school, and we have regression, which is predicting one variable based on another. So we are looking at does study time predict exam score? We are looking at the regression. We are looking at the relationship or the correlation of some sort. Regression is actually using the past to predict the future. It's much more predictive. Of course, I already explained that for quantitative data that has to do with numbers, whether it is discrete, that means I can take on only one value, such as age and the likes, or continuous that can take on many values, such as height. Height is like one, it can take on many value, 15.9, 1,000.1. It can take on, it's continuous. So this hypothesis testing or statistical test is used for quantitative data. We have the t-test, the ANOVA, the chi-square, the correlation, person correlation, and the regression analysis. And then we have the qualitative data, which is for nominal data or ordinal data, data that does not take on numerical value at all. We have the Mann-Whitney test, we have the chi-squared, we have the binomial, we have the Spearman-Wilson test. We have the qualitative data to test for this nominal or ordinal data. And then I will give you I'll send it Google Sheets for you to open. Let's just look at, see that I have participants, age, gender, weight, dose, their serum level concentration, the heart rate, and the adverse effects. I have run the descriptive. So we can see some of the parametric testing, right? T-test, ANOVA. I can go to exploration and they run their descriptives. I can see that I've run the descriptives already. It gave me the frequency table, the number of male and female, their age, weight, and everything. It gave me the mean for male and female group, gave me the standard deviation. That's running through any formula in Excel or using my manual calculations. And it gave me the descriptive plots. This is an area plot. There are different kind of plots. You can use bar charts, you can use any plots that you want. And then if you can go further, I ran descriptive also for the adverse effects, the descriptive plots, and then I moved to independent sample t-test. You can see from this t-test that I am comparing independent sample t-test is when you are comparing the mean of two different groups, such as male and female. I ran it on this software. It's back end. It has all the languages, the programming languages, and everything. It runs on R programming languages to run up the calculations for me, and it gave me a summary table of the statistics, of the degree of freedom, and of the p-value. So you can see that my p-value is 0.111. That means there is no statistical difference between the heart rates of male and female. I cannot infer from my mean or from my standard error. I can only infer from my p-value. So I fail to reject the null hypothesis. The null hypothesis states that there is no statistical difference between heart rate in male versus heart rate in female. So I've run my independent sample t-test and my p-value, this is p, is 0.1, which is greater than 0.05. If my p-value was less than 0.05, that means there's a significant difference or significant evidence of the heart rate in male and female group. I ran my assumption to test if this is a normally distributed curve. So I test for homogeneity in the data. That's for advanced classes. I would show you how to read that. It's very, very important before you run your testing. But this is just to show you that you don't have to do manual calculation on Excel, but you can run into any statistical software and then you can analyze the data. Run, first of all, don't forget to clean your data, run your descriptives, and then state your non-alternative hypothesis, and then run your inferential, depending on your research type. Whether you're doing a t-test, ANOVA, or regression, you know, and of course you can then come to a conclusion. So it is from the p-value I got my conclusion that there is no significant evidence or there is no significant difference between the heart rate in male and the female group. That's all.